Hello, and welcome to this second supplementary part of Lecture 13. What we'll be talking about in this part is a fun paradox that emerges for the most natural, naive conception of the nature of sets. In order to kind of set it up, it's helpful to cash out this naive conception of set theory. So, I mentioned earlier the axiom of extensionality. And extensionality, what it does is it gives us identity conditions for sets. It tells us if we've already got sets, whether they're identical, if say they have all and only the same members, or if they're distinct, right? Because if they differ in members, then we can infer they must not be identical. But of course, that just tells us when two sets that we already have are or are not identical. It doesn't really tell us what sets there are. That we need something else. So, according to naive set theory, we have a story here. And this is where we can enter into appeal to the axiom of comprehension. So according to the axiom of comprehension, we can say that for any condition C, where C is going to be any first-order formal logic sentence, so any FOL sentence, there exists a set S such that for all X, X is a member of S if and only if X is a C. That is, X makes C true. So really, right, the axiom of comprehension basically says, hey, if you can come up with any kind of predicate, well, anything that satisfies the predicate, there's going to be a set of all and only the things that satisfy that predicate. So the axiom of comprehension and the axiom of extensionality together constitute what came to be called naive set theory. Now, there was a lot of hope when set theory was first developed that this combination, that basically just accepting the axiom of extensionality and the axiom of comprehension would basically give us all of mathematics. And it actually looked pretty good for quite a while. Because, again, there's so much we can do with just that very basic set theory that we talked about in the previous lecture. Of course, we need these two axioms, one to tell us what sets there are, and one to tell us, hey, what's the identity conditions for sets? But with them, we could get out so much of mathematics. The problem is, there's a real big issue lurking here. Naive set theory faces a really horrible and very famous paradox first invented by one of my intellectual heroes, Bertrand Russell. So, Russell's famous paradox shows that we cannot consistently hold naive set theory. In fact, naive set theory cannot be the foundations for all of mathematics if we want to be consistent. So, to kind of get a run at the paradox, it's helpful to think about something slightly different. And you might have heard this before, but a slightly different way to approach it is to think about barbers. So, consider a small town, right? And really small town, who's only got one barber. And this barber is a very fastidious person, and the barber follows a strict rule. And we'll say he's a he, just for ease. So the barber's strict rule is that the barber shaves all and only those people who don't shave themselves. So the barber will shave anyone, provided that they don't shave themselves. Of course, he shaves everyone, and all and only those people. So, fair enough. But we hit a problem, as we ask, who shaves the barber? The barber is a member of town, and he might want to be shaved. So who shaves him? Well, let's look at the barber's rule. The barber's rule suggests that if the barber doesn't shave himself, right, well, then he would be one of those people who doesn't shave themselves. So then he must be shaved by the barber. But he is the barber. So if he doesn't shave himself, then he must shave himself. Well, that's not good. So let's try the other option, right? So cool, maybe he shaves himself, right? And then it's sorted, right? He wakes up every morning, lathers up, moves it off. Well, if he does shave himself, then he violates his rule. If he does shave himself, then he's not a member of the set of people who don't shave themselves. So the barber must not be shaved by the barber. But the barber does shave the barber. So if he does shave himself, then he must not. And if he does not, then he must. We're kind of damned no matter what we do. And this is again because of the rule he has, because the barber shaves all and only those people who don't shave themselves. So if he doesn't shave himself, then he must be going to the barber, but he is the barber. Meanwhile, if he shaves himself, then he must not be being shaved by the barber, but he is the barber. So no matter what happens, we end up in a contradictory situation. Now that's just a kind of silly kind of version of it, but in effect, that's Russell's paradox. So we can think about it this way. Given that sets can themselves be members of sets, there's nothing to stop some sets from being members of themselves. So we'll just say have M be the set of all sets with more than one member. Well, obviously, right, M is then going to be a member of itself because there's a whole slew of sets with more than one member, so M must be a self-member. Similarly, if we think about set N, right, let's have N be the set of all things that aren't buses. Well, sets aren't buses, so N must be a member of itself. Now, running with this idea, let's define R as the set of all things that aren't members of themselves. So basically we can express it this way, right? It's the set of all x such that x is not a member of x, right? So clearly M and N, as we define them up there, aren't going to be members of R. And the condition we've defined here is effectively is not a member of itself. And note, given the axiom of comprehension, we know that this condition should define up a set. There should be this set R, right? Because we've specified a condition, and the axiom of comprehension says for any condition you pick out, there's guaranteed to be a set of those things. Here's the problem. So we've got our set R. Is R a member of itself? Well, if R is a member of itself, then it can't be, because R is defined as the set of all things that are not members of themselves. So that's bad. In contrast, so if R isn't a member of itself, then it must be a member of itself, because again, R is the set of all things that are not members of themselves. So R would be a thing that's not a member of itself, so that would then have to be a member of itself. So no matter what you do, you end up in a contradiction. If R is a self-member, then it must not be. And if R isn't a self-member, then it must be. And there's no way out here, at least no obvious way out here. All because what we've done is we've specified this condition, which by the axiom of comprehension is guaranteed to deliver us this set. So this was the really horrible paradox that Russell identified in the deep, dark-hearted, naive set theory. And when he pointed it out, it kind of broke poor Frege's heart. Because Frege had built up this beautiful edifice of reducing all of mathematics to naive set theory, and it just didn't work. Which is a shame. But this is Russell's paradox. It's an amazing little paradox here. So Russell's paradox demonstrates there's something rotten in the heart of naive set theory. We can't just have a story about sets that is entirely understood in terms of the axiom of extensionality and the axiom of comprehension. Now, set theorists have tried a bunch of different fixes, and there are lots of different ways to go. So one option is we can distinguish between classes and sets. So sets could be understood in terms of something like naive comprehension and extensionality, but once we hit a certain kind of level, we're no longer talking just about sets. So we can't really buy the axiom of comprehension as it stands, but we can say, right, for any condition C, you're guaranteed to get a collection which might be a class or it might be a set. This is a move. It's not really clear how successful this is. This was actually Russell's initial attempt. Right. Another option might be to restrict membership. So we modify the axiom of comprehension and we restrict memberships just to sets that can't be members of themselves. Now this seems like a move to make, but again, it blocks off some pretty intuitive sets, like for example, my set N, where N is the set of all things that aren't buses. That seems like a pretty good set, and that seems like it probably should be a member of itself, because sets ain't buses. Right? Just try and take a set to the hospital or something, and you'll find out it's not very helpful. Right? No matter how long you wait at the stop, it doesn't pick you up. Right? So again, this is a move. It's not clear. One move that's been favored quite a bit is to adopt what's often called an iterative hierarchy approach to set theory. So the idea here is that we can apply the axiom of comprehension, but only at certain levels. So what we can do is we take our elementa and we generate all the sets we can from them. And that now gives us another layer, namely all the sets we've got from our individuals. Now for our next layer up, we can apply our set theoretic machinery to everything that we got from our first iteration and the individuals. This gives us the next layer up. And once we have that, we can apply our set theoretic machinery to everything below that to give us the next layer up. Now, by adopting this kind of hierarchical approach, you're not really allowed to apply the machinery to a set that you're constructing as you go. And this is a good approach. It seems to be very well. It works very nicely in lots of cases. There are some really interesting kind of mathematical justifications for buying into it. It runs into its own problems. It's a neat kind of option. Another view, and one that has been explored kind of relatively recently, is to deny the idea that we need to have consistency here. So one option is we can adopt a non-classical logic. So this is something we'll talk about in lecture 14, where we allow for true contradictions. And this is a very radical move. It's been developed a little bit recently in some philosophers of logic, by some logicians and some philosophers of mathematics. It's an option. It is a view. But really, what's important is no one thinks that naive set theory can escape Russell's paradox. It is a big problem. And it's a problem that set theorists need to face up to if they're going to use this beautiful, extremely powerful machinery. Cool. So that's Russell's paradox. What we're going to do in part 3 is we're going to turn to and look at natures of infinity. So we'll use our set theoretic machinery to talk a little bit about degrees and different types of infinite sets. So thank you very much. I look forward to seeing you in the next part.